Today's lesson is the discovery of the derivatives for the 6 trig functions we remember from pre-calculus. I'm going to start with a visual approach for the derivative of sine and cosine. If I look at the sine curve right here in red, this is also the line y equals x. I am looking for slopes, and I'm trying to figure out the connection with slopes. Well, right here at the origin, I had the computer draw the tangent line at 0. The slope at 0 on the sine curve is a slope of 1. Notice the graph of cosine is hitting here at 1. I follow along. I have positive slopes, and they are getting less and less positive as I progress towards the maximum. So I start at 1. I'm getting less and less positive as I head towards the maximum at pi over 2. And notice when I'm at pi over 2 at my maximum, the cosine graph is at 0. After that, I am decreasing, so I have negative slopes getting more and more negative. The derivative of sine is cosine. The cosine curve is up here in the blue. Starts off with a horizontal tangent. The sine curve is at 0. I'm over here at the pi over 2. If I had the tangent line in here, the tangent line would be a slope of -1. The sine graph, though, is at +1. And in between, this is decreasing. So I'm getting steeper and steeper in a negative fashion. But this is saying getting more and more positive. Then I look at this side over here. Slope would be 1. The cosine, or the sine curve, is at -1. So the derivative of cosine is negative sine. An analytic approach to the derivative for tangent is to look at it instead of as tangent, but as a quotient of sine x over cosine x. Using the quotient rule, we have our low, d high, I just learned the derivative of sine is cosine, minus the higher function, which is sine of x, d low, taking the derivative of the cosine, cosine goes to negative sine, all over denominator squared. Simplifying the numerator, that's a cosine squared, that is plus sine squared. I'm looking at the top and realizing that's very familiar. What is that? That's our identity from last year. It's 1. I have 1 over cosine squared, so now I get to the final answer. Who's the derivative of tangent? The derivative of tangent is secant squared. And if you don't want to have to rederive them over and over again, then you commit them to memory. Or you just do a quick derivation. All the rest of the trig functions can be done the same way using a quotient rule. But I'm just going to give them to you in the interest of time. The derivative of secant is a fun one. I always say it's secant, kind of it's like a rhymey little songish kind of thing. So secant, it repeats itself times tangent. Cosecant, and another helpful little tip, is all of your c trig derivatives. It's like going under the sea, and it's below sea level, so the c's go negative. So the derivative of cosecant, kind of paralleling, is itself times cotangent. And the derivative of cotangent, I see a sea, I'm going under the sea. You can think Little Mermaid, I'd be singing to you in class right now. Negative, and then derivative of cotangent is negative cosecant, squared. So these are the 6 trig derivatives that you want to commit to memory. Using them, we're going to start off with finding the equation of the line tangent. Anytime I need a tangent line, I need a point and I need slope. I have an x value. I'm going to find the corresponding y value, so I have my point. So y at 3 pi over 2 is 3 pi over 2 times the sine at 3 pi over 2, which is negative 1. So we end up with negative 3 pi over 2 for the y value. In addition to a point, I also need the slope. In calculus, slope is derivative. I'm looking here, it's got a trig function being multiplied by the linear function. The minute I see a product, I go for product rule. First, derivative second, plus second, and the derivative of x is 1. I need now the slope at our particular point because that's where we want to create the tangent line. So I'm going to plug in my 3 pi over 2. The cosine at 3 pi over 2 is a 0. The sine at 3 pi over 2 we said was a negative 1. Putting it all together, y minus the y value is negative, so it's plus 3 pi over 2, is equal to my slope, which my slope is a negative 1, so I'm just going to throw a negative sign in front to lead off with the slope, times x minus the x value, which is 3 pi over 2. Finding the points on the curve of the tangent function where the tangent is parallel to this particular line. Well, if it's parallel, then they have to share the same slope. So I'm going to say 4x minus 2 is equal to y, so I'm in slope-intercept form. That means if they're parallel, that slope of 4 is the slope on the tangent graph. So I go to my y equals tangent, I take its derivative. The derivative of tangent is secant squared. And that, if I'm matching slopes, because I'm parallel, would have to equal 4. If it's easier, instead of thinking about secants, we think reciprocal trig functions. So I'm going to take the reciprocal of each side. And then I'm going to say cosine of x is equal to a half, but not just a half, because that's squared. We have our plus or minus. Then I have to pick on this given interval. When is the cosine equal to a half? X equals, let's start with quadrant 1. That's probably the easiest point of reference. So when is the cosine equal to a half? That's going to be at pi over 3. That's your 60. And then if I'm going backwards, which is going to quadrant 4 backwards, then I'm going to say negative pi over 3 is the other spot. Finding the points on the curve means I need the y value at pi over 3 and the y value at negative pi over 3. So I'm now looking at the tangent of my 60. Tangent is opposite over adjacent, so I have root 3 over 1, or just root 3. My pi over 3, but in quadrant 4, is going to be the opposite side, which is a negative root 3, over the adjacent side, which is a positive 1, end result negative root 3. The points on the curve will be pi over 3 with root 3 and negative pi over 3 with negative root 3. Differentiating. I see a quotient. It cannot be simplified because we have two terms in the denominator. Y prime equals low, as is, d high, secant tangent, minus the higher function, secant x, d low, derivative of 1 is 0, derivative of tangent is secant squared, all over denominator squared. Now technically that is my derivative. However, if it's a multiple choice, you got to make it match to whatever format is given. Chances are it wouldn't be written in this format. I notice that this is all my front left that has a secant. This has a secant. I'm going to take it out because I'm kind of thinking ahead about my identities, and my identities involve squared trig functions. So I'm going to pull out that secant, so then I have some squared trig functions to analyze. What am I left with? 1 times tangent is tangent. Tan times tan plus tan squared minus what's left here is the secant squared over 1 plus tan x being squared. Anytime we have those trig functions squared, you're thinking those Pythagorean triples. You may or may not have them memorized. If you do, you can go right to the answer. If you don't, here's a little helpful tip I learned way back in the day, and I use it all the time. I know sine squared plus cosine squared equals 1, and that's the only identity I remember. If I want to create any others, I simply just generate it by dividing by what I need. I have tangent and secant. Both have cosine in the denominator, so I'm going to divide through by cosine squared. Well, what do I get? Sine squared divided by cosine squared is my tangent squared. This is a 1. 1 over cosine squared is secant squared. Alright, if I look at it, a little manipulation, move the secant squared here, the 1 here, that tan squared minus secant squared is really just a negative 1. So we have secant of x times tangent of x minus 1 over 1 plus tan of x being squared. We're going to go back and revisit some limits from the start of the year, but now we're going to do them with trig. There are key limits that you want to remember, and if it helps you, you can think about this visual. I'm analyzing right here near 0. Well, what's going on near 0 for a sine function divided by the linear function x? If you notice, they're both equal to a value of 0. So technically, this is the indeterminate 0 over 0 form. And normally, we would do some algebraic maneuvering to get my answer. I'm going to do it a little differently. I'm going to say zoom in. If you want to type it into your calculator and keep zooming in and zooming in and zooming in, these are matching each other. They are very, very, very infinitely close to matching each other. So I'm taking a particular height and dividing it by the same thing, basically. The ratio is 1. When you have matching heights and you divide them out, the ratio is 1. Well, if I flip it around, it's still matching. Even over here, it's matching negative values. That approaches 1. If I do any type of horizontal shrink or stretch, if I do it inside the sine as well as the linear, they're matching. Focus in on 0, pick any numbers you want. Again, you have matching heights in the positive direction and matching heights in the negative direction. That means it goes to a ratio of 1. How does that help us out? When I go to evaluate some of these limits, then I'm going to use that fact that you have a ratio of 1 whenever it's a sine function over the corresponding linear function to match the angle. This particular problem, both of these pieces are being divided by x. So I'm going to do an algebraic maneuver where I split the fraction so that I'm showing each of them is being divided by x. That's what I want. Well, x over x here is canceling, and what am I left with? I'm left with an e to the 0. Sine of x over x, we just discovered, as you go close to 0, and only 0, that piece goes to 1. So we end up with a limit answer of 2. My next one, it kind of borders the idea of a proof when you do these. You're seeing sines and sines, but I don't see any linear functions because I'm trying to make that special ratio that goes to 1. These both go to 0, but it's not that special ratio that we have here. I'm going to make that special ratio happen because I can rewrite any fraction as the product of as many factors as I need, as long as I create an equivalent expression. So I'm going to take my sine of 5x, and we discovered up here, if the angle matches the linear function, it goes to a 1. I'm going to take the angle of 5x and say I ideally want it over 5x, but I don't have that linear factor of x. So I'm going to make a little note to myself that I box it out and say I put in an x. So I have to account for that. And then I'm going to look, I've used this, I haven't used the sine. Well, again, sine of the linear function, to make it match and go to a 1, what do I need up here? I need an 8x. I don't have either one up here. I'm boxing it out to say I put that in. And then I call this thing over here my balancing fraction. I have to balance out whatever I put in. This x is balancing with this x. So that's a 1, and that matches, and it's okay. This 8 I also put in, but there's no compensation for it. So I need to right now compensate for the fact that I put in an 8 to create a special 1. Everything now is accounted for, so I'm just going to fill in with a 1, because that won't change the value of the fraction. And when I go to evaluate this limit now, I can say comfortably, this ratio goes to 1, and the last ratio is 1/8. So my answer for my limit is 1/8. I have tangent. There's no discussion up here of tangent, only of sine, because sine is the one with that special property. What I'm going to do is rewrite the tangent as sine over cosine, so I can introduce that concept of a sine, so I can apply my new rule. The limit is x goes to 0 of, and again, I'm going to create different factors that are equivalent to this, but a different form. I start with my numerator. I have the sine of 9x. Ideally, what do I want down here to make it go to a 1 ratio? I want a 9x. I want that matching linear factor to the angle. The cosine is in the denominator. This is not a sine. When I plug in a 0, cosine of 0 is not 0. Cosine of 0 is a 1. So that means this is not a problem in a fraction. There's no balancing needed when you have a cosine, because it's not dividing by a 0. This 2x, if I'm dividing by 2x, it's like multiplying by 1 over 2x. I have to go back and say, oops, I put that in, so I'm going to compensate by saying box that out. This was in the original, this was in the original, this is in the original. That means I have to balance with a 9x. I'm kind of looking ahead strategy-wise. I've got some ones, and then, ooh, that's a 0. That's a problem. But if I balance with putting 9x in the numerator, now I've compensated for what I put in, and the expression is equivalent to my original. I can say 1 times the ratio of 9/2 when we simplify. We get 9/2 for the answer. This one you want to be looking at as, oh, it kind of looks like what we talked about up here, but this one has a shift moving to the left. Well, how does that impact us? What I'm going to do is I'm going to let u equal the inside, so I kind of can make it match what I have up there. So I'm going to say u is equal to the quantity of x plus 6. Then it becomes the limit as, and I'm going to fill this in a moment, sine of u being divided by that u quantity. Well, this is just like saying sine of x divided by x. We know that ratio, but when do we know that ratio? It's not at negative pi over 6. So this is where it comes into play here. I'm going to say, okay, if x is approaching negative pi over 6, I put negative pi over 6 in here, and that tells me what u approaches. So if you put negative pi over 6 in here, that means the u value is approaching 0. Now this whole thing matches exactly what I have up top, and that ratio goes to a 1. This limit notation hopefully looks very, very, very familiar to you. Kind of like an f of x plus h or an a plus h minus, this is the value of a function at a particular point. Ooh, is it that input of pi over 6? What is the sign of pi over 6? It is 1/2 all over h. This setup right here is equivalent to finding the derivative or slope of a particular function at an input value. This is the a or the x, the input at pi over 6. So the question is, well, what's our function that we're deriving? F of x, the function where I'm putting my input in, is the sine function. So f of x is going to equal sine of x. Its derivative in general, and again, strongly encourage you to do derivatives in general before evaluating it at a point. F prime of just x is the cosine of x. F prime at pi over 6 now is the cosine of pi over 6. That's the cosine of a 30, which is a root 3 over 2. Which of the following would have no horizontal tangents, no flattening? Well, I look at sine and I look at cosine to start, and those we know are the traditional wave functions. Those have lots of horizontal tangents. So that means those are off the table. Tangent of x. Well, let me think. I don't remember tangent's graph. Let's look at the derivative of tangent. Maybe that'll give me some information. Secant squared of x. I really do remember tangent's graph. I'm playing pretend. So y prime equals secant squared. And then, well, how else could I look at that? That's the same as saying 1 divided by cosine squared of x. In order for a graph to have a horizontal tangent, that means y prime at some x value has to equal 0. Well, if I look at my derivative here, I have a 1. I can never make the numerator equal to 0. So this graph would not have any horizontal tangents. And if I kept going and analyzing, y prime equals secant tan, sectan, that's Mrs. Jasic's favorite derivative, sectan. And then if I look at it, it is 1 over cosine times sine over cosine. But now I've just created a scenario where I can cause the numerator to be 0. So it would have a horizontal tangent. E, y prime is equal to 1 plus cosine of x. Can the derivative equal 0? Because that's a horizontal tangent. And then I'm looking here. Well, this would mean, when is the cosine of x equal to a negative 1? And hopefully you're all shouting out, oh, it's at pi, it's at pi. Gone. And that's 3/5.